Okay, state the principle conservation of charge. Uh, w- Conservation of charge actually will be same as what you have learned in momentum actually. Next, in net change charge, this is charge, not change. Net charge Qn, net charge of an isolated system will always remain same. So before we have uh, a some amount of a charge, and after the charge will be same. What happened to both of them? Uh, Q1 plus the Q2 will be same as after there is Q1 plus Q2 before will be same as Q1 plus Q2 after. What happened when they are isolated? The before and after the charge will be remain constant. There will no uh, there will no uh, there will no change of the charge. It's logically the charge will not be uh, not disappeared to other side. Okay. B. What is equipotential surface in electric field? Equipotential surface is a potential surface. It's an imaginary surface that is containing all the points with the same electric potential. So if we have let's say we have a sphere, a charge sphere Q, okay. So all the points, and this Q is a perfect sphere, and all the points over here we have a same EQ potential because it has the same value of potential. Okay, and this side, okay, and this side, you have another equipotential surface. This is actually a 3D actually. Okay, potential surface where this point, the blue point doesn't have this. Is a different value of the green lines. Okay, so number two, there is one special characteristic of this equipotential surface that when you move a charge, between, I'm using another color. When you move a charge between the equipotential surface, let's say from here to here, okay, there will work done will be equals to work done okay equals to zero. Okay, there are no work done. Or if you move from this point to this point, work done equals to zero. So you can put one more points over there. There is a no work done. Okay, no work done in moving an electrical charge from one point to another point on the surface. Okay, so that's there will be a second point, but because I think it only has one mark, right? It's one mark. I think it will be sufficient if you have answered the first part only. Okay, but if you have two marks, I think you have to elaborate what is the work done to move one point to another point. Okay, C1, uh, a small conducting sphere P with radius P, radius R, carries a charge Q. The conducting sphere is placed at the center between the two parallel metal plates. We are connected to the terminals of the battery as shown. The distance between the plates are 3 cm and the force experienced by conducting sphere is 5 times 10 power negative 4. Okay, the distance between, okay. What is charge density inside the sphere and the surface in system Q and R? So you have remember when we have learned so many in the Gaussian law. Okay, so Q and R, uh, Q and R, if we have a graph at the inside of the surface of the sphere, either it's hollow or solid, there will be 0 E, and at the surface of the sphere will be increased and then drops down in the pi 1 over pi r squared. Okay, And same situation with the behind, back and in front of the behind of the side and the inside of the sphere. Okay, so charge density inside the sphere, of course, will be 0. So it didn't mention here. So C1, charge inside sphere equals to 0. And number 2, at the surface, you use the Gaussian law or the Gaussian surface. You have a Q charge charge density sigma equals to Q over 4 pi r squared. Okay, you can use a Gaussian law. You can uh, derive the surface charge. We call this charge density on the surface. Okay. Okay. Number 2, if the sphere P comes to the contact with another conducting sphere uh, S, which initially uncharged, and the radius twice of P, what is the force of the sphere P after the sphere S has been removed? Okay, this is a common misconception of the student. Okay, why is a common misconception? Okay, it's because students tends to imagine that when we have a tool, let's say we have a Q one as a sphere of Q1, and then we have a sphere of Q2. Okay, and this is a charge sphere, charge, and this is a charge. Okay, with some amount of Q. Okay, I will put Q1, Q2 because it's a different charge amount. Uh, Now when we put a let's say we have a conductor, a wire or conductor throughout the that is connecting both sides. Let's say we put a wire here. Okay. Students uh, tends to uh, imagine that the Q the Q will be equilibrium. Means that Q1 1 plus Q2 divided by 2. So this one will be on this side. This one will be side. Okay. So this is a very big mistake because it is not the 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 amount of Q1 divided by Q2 in on the each side. It is the V actually. Okay, so Q 1. Okay, on I say this is sphere 1. Sphere 1 charge on Q or sphere 1 will be not same as charge on Q on sphere 2 after the after the wire are connected. It is V on the sphere 1 will be equals to V on the sphere 2. The potential will be same, but the charge on the sphere will be different. Okay, so by using the potential different, the potential different, then we can find how much the Q on the each side. Okay, so remember that. Okay, so now from V1 equals to VSQ2, VS1 equals to VS2. Okay, I have to remove all this writing over here. Okay, okay. So VP equals to VS. This is a good start. VP equals to VS. Q1 over R equals to KQ1 over 2R. Because why 2R? Because it has a 2 times of the radius. Okay, Q2 has twice the radius of P, so Q to R over 2R, and you have Q2 equals to 2Q1. So actually, it says that on the right side, on the VS, on the S sphere, we have two double the Q from double the Q from Q2. Okay. Um, So since Q1, Q2 equals to Q, Q1 plus Q2 equals to Q, this is applying what we have learned in 19A. Okay, uh, principal conservation of charge 19A. So since Q1 plus Q2 equals to Q and Q1 plus 2Q equals Q, okay, this is before and this is after. So Q1 is equals to 1 over 3 of Q. Okay, so E remain the same and F EQ, okay, equals to E 1 over 3Q. So you have answer over here, that is 1 over 7 times 10 power 9 Newton. This is correct. Okay, so this is why you have a 4 marks. First of all, you have to start with a Vs equals to Vp, and then from there you have to use a conservation of uh, charge Q, and from then you have to find the F. Okay, so that's why we have a 4 marks for that question. Okay, we go to number 3. The sphere P again is charged in the Q and separation of plates increased to 4 cm. What is the force experienced by sphere P? Okay. Uh, Number 3. So distance will be D2. You put a D2 because it was increased to 4 cm. Okay, distance is 4 cm. So E is V over D. Okay, V naught means that I think it means that V naught is the original potential difference. Okay, so D over 2, V naught over 4 cm. So V naught is equals to 4 E2. Okay, so E naught again equals to V naught over 3. So V naught equals to 3 E naught. So okay, this is the what I call the proportional between V naught and E2, and this is V naught and E naught. You can see the difference. In V naught, this is V naught and E2, and this is V naught and E naught. So correlation between them. So for E2 equals to 3 E naught. So E naught equals to 3 over 4 E naught. So you have a force that is 3.75 times 10 power negative 4 Newton. This one is correct. Okay. So okay, I think we go to now question. Any question on this? Uh, at this point, any question, everyone?
No, sir.
Okay. So number 4, another two identical batteries are joined with series, means that we put two more batteries on the circuit. Okay. Uh, if the charge on P and the split separation will be same as C3, or okay, same as this one. What is the force explained by P? Okay. So two batteries is 2 V naught. Actually, this answer is wrong. Okay, we start with new one. So we have 3 times V because we have 3 batteries. Okay, so we have 3 V actually. Okay, so new, so I put as a, how to rename this one? Mm, New potential difference. New potential difference equals to 3V because we have 3 batteries. And E2, new electric field equals to uh, E2 equals to 3 times V because we have 3V. 4 times 10 power of negative 2 is the distance between them, V over D. And then equals to 9 over 4 E. Okay, 9 over 4 E. So the force that is F2 equals to QE, and this is EQ. So equals to Q and times 9 over 4 E, and 9 over 4 we put as 9 over 4 QE, and Q is actually 5 times 10 power of negative 4. Okay, so we can say that it is uh, because it's original like Q naught and E naught, so we have explained it will be 5 times 10 power negative 4 Newton. So we have uh, the ratio between the new and the old. This is the original times the new ratio, that is 9 over 4. Then we have 1.125 times 10 power negative 3 Newton. So this will be the answer. I think he made a mistake because he was assuming that we have only 2 batteries. Actually, we have 3 batteries. This is the biggest mistake there. Okay, if you have 3 batteries, I think he can get the right answer. Is Wang Lam here? The one who did this question? Is this here? No. Okay. Next, question number 20. Alternating voltage is represented by V equals to 3.0 sine 218t. Okay. So what is the frequency? RMS voltage for this AC. So we know the uh, general equation formula for sine for the sine graph will be V equals to V naught sine omega t. Okay, or we can say that 2 pi ft sine 2 pi ft. Okay, so the frequency, you can determine the frequency. Okay, I'm using red color, easier to see, to differentiate which one. So V naught sine omega t 218t, so omega is 218 and V naught is 3.0. So V 2 pi f equals to 218, so it will be 3.4, 34.7 hertz. Okay, this one correct. So Vrms equals to V naught over 2 is very basic equation. So 3.0 times divided by square root of 2, so 2.12. So this one also correct. So 2 marks over here and 2 marks over there. Okay. B. 20b, the AC referred in A is connected to the field inductor of 10 millihenry. Explain why this conductor produces EMF will oppose a supply voltage. Okay. Why is opposed to supply voltage? Uh, so when the AC flows in the inductor, magnetic flux increases through the conductor very sinusoidally. Okay. Uh, okay. First of all, mention about uh, magnetic flux. Okay. Magnetic flux through conductor is AC. So it means that there will be up and down, up and down, up and down. So because it's going up and down, there will be change of magnetic flux. That's d phi over dt. Okay, so this is number 2. You have to mention that because we have a magnetic flux is up and down, up and down. So there will be change of magnetic flux equal d phi over dt. Because we have d phi over dt, okay, because of this, uh, it will be produced by the Lenz law. Okay, there will be by Faraday's law, the Faraday's law and the Lenz law. Okay, it will produce a electromagnetic induction. Produce electromagnetic induction, and plus the back EMF. Okay. So this is the whole thing you have to say inside the, you have to mention inside the inside the answer. First, material flux. You say material flux when the supply voltage enter the inductor produce EMF that is equal to supply voltage of precipitation maintain the current. No, no. I think you only get 1 marks over here because maybe he only say about the third uh, point. He didn't make any. He didn't say mention about the second, and he didn't say about the first. So I think he can only get around 1 marks because of this. Okay, so you have to mention 1, 2, and 3 points over there. Okay, so you may ask me, do you have to explain what is the Faraday's law and the Lenz's law? I think not because it has only how many marks here? Because in only 3 marks, I don't think you have to explain what is the define what is the Lenz's law and Lenz's law and the Faraday's law. You only say that you can explain that because of the Faraday's law and the Lenz's law, it will be the electromagnetic force will be induced, and then the back EMF will be happen. Okay. So B2 at particular instant the supply voltage is 1.5. What is the back EMF in the inductor at that instant? Okay. So what is the back EMF at that instant? So E big EMF. Okay, EB. Red color is better. EB equals to negative L di over dt. Why we have L? Because it's a pure inductor. Di over dt. L given, V given, V not given. Uh, so we have answer is 1.5 volt. This is correct. 1.5. Okay. Next part is reactance. Okay. What is the RMS current that flows in this inductor? Okay. So you have to find the reactance. Reactance is similarly like a resistance that is opposed to the current flow in the circuit. So XL equals to 2 pi FL, and because you have substitute everything, you have 2.18 ohm. RMS current is VRMS divided by XL. So it's 2.12 divided by 2.8, then you have 0.972 ampere. Okay, this is correct. So you have to full marks of this. How many marks here? There's 2 marks. Okay, correct. Uh, Hanky, right? Who's the one who did this? Hanky, are you there, Hanky? No.
Yes.
Okay. So most of the answer you given is correct. Okay.
Mm.
Congratulations. Okay,
Mm.
but C1, it says that based on the graph C1, explain why the average power supply inductor is a 0. Oh no, it says select a graph for variation of voltage across conductor in a time. On the same axis, sketch a graph of variation of current after this time. Okay, so you have a good graph over here. V is which one is lagging, which one is leading. Uh, this is a graph of inductor CIVRL. So in voltage will be leading and I will be lagging. So V is leading, I lagging. So you can see here V on the on the 0 and I will be still on the bottom. Okay, this one correct. So V has a 90 degrees, pi over 2 of leading. Okay, so the graph will be correct. You have the 3 marks over there. Based on the graph C1, explain why the average power supply inductor is 0. Okay, based on the graph below, the spherical need to predict power supply and which causes power through inductor because no, this is not the answer. Okay, if you can draw back. You can trace back all these graph. I think which one better? All this graph, or you can draw on on that graph easily, or you want to copy, you can copy. You can say that okay, this is up, down, up, down. This is V, this is I goes up and goes down here and goes up again and goes up there. Okay, you can explain that in the P graph. In the P graph, okay, P graph will be going down and goes up and go down and goes up and goes down like that. Okay, in the P graph for the whole T1, for the whole, this is where? This is T over 4, right? T over 4. You can see that at the T over 4, 0 to T over 4, power is uh, negative, means that return to the power supply. Means that it gives out power back. At this point, it gives out power back to the circuit. It doesn't absorb the power, but it's given back the power to the circuit. Okay. You remember in the inductor, the work or the energy was stored in the form of magnetic force. Okay, magnetic force is not, it's not like capacitor where energy was stored in the electrical force. This is magnetic force B. At this point, from T4, from T over 4 to T over 2. So at this point, T over 4 to T over 2, this is power will be is positive. It means that power is absorbed absorbed uh, absorbed from the power supply. Okay, now is absorbing the power back. Okay, so we have two cycles. The first cycle is return. We are returning the power, and then is absorbing. So the mean power, because it's a mean, right? It's a mean power. It's average. It will be 0. So that's it. Okay, that's the way to answer this kind of question. Okay, any question? Any question, anyone?
No, sir.
No. Kishika, Abi,
No, sir.
no. Jahan, Kyomin, any question? Hankit? No. Okay?
No, sir.
No. Okay. So going to release the fifth model paper. Okay. So we take turns. Usha, Abi, Weng Yu, Kihang, and Hankit already done. So we have to find another student who doesn't do anything, like who haven't done anything, like Keshika, who's it? Jahan and Xiaomin, to try to answer, and then we discuss in the Zoom. Is it okay? Is it okay,
Okay,
everyone?
sir.
Okay. Ah,
Okay, sir.
Abi okay ah?
Yeah, not me, sir.
Okay. Okay, see you. I'm going to release the fifth model paper. Okay, see you again.
Okay, sir. Thanks, sir.
We have class tomorrow, is it? We have a class
No class, sir.
tomorrow. No class ah?
Hey, got class, got class.
No class. Okay. So see you tomorrow.
Okay, sir. Thanks, sir.